This morning, Yusef is going to tell us about a technique for finding habitat associations using WWBIC species records that he has developed as a result of project work. Thank you, Yusef.
Thanks, Kate. Just share my screen. I'm using I'm signing two devices here, a laptop and also a desktop computer. If everyone can see and hear me and the internet is fine from here on the laptop, I'll go ahead with the presentation on this for now. And then I can always jump over to the desktop if that isn't working properly. So everyone can hear me fine and is seeing the slideshow fine at the moment?
Yeah.
Yep. Great.
It's not full screen yet, though.
No, I'm just
That's fine. Yeah.
Great. Okay. So there's a fair bit to cover in this presentation and a little bit of time, so I'm just going to dive into it. So this is a work in progress, what I'm presenting here, and it's developed through a lot of project work that we have undertaken as Lurk Wales over the past year. So this really started out with the Welsh Landscapes for Rare Bumblebees project that Colin has already talked about. As part of the work for that, I created habitat maps based on the associations of rare bumblebee records with phase 1 habitat classes. And we use that partly to map, where to for this project, and also to overlay that with areas of low recording. So here we can see areas of the core habitat identified by that analysis, showing square over squares where there's relatively few bombus records as a means of targeting recording to find hopefully new sites for these rare species. From the back of that, Cofnod, the North Wales Record Centre, got in touch with us and asked if we could use this method to basically develop some habitat suitability maps from the data for a local nature partnership in North Wales called BioNet, which covers the northeast regions. And the method was refined to produce, this map that you should be seeing in front of you now for adder. We did this for 4 species as a pilot. And we've now been approached from someone in Brecon Beacons to do a similar method for planning conservation work for curlew, and we'll be refining some more environmental variables into that as alongside just habitat classes. So the work, is I'm just seeing some, sorry everyone, just seeing those comments about annoying chatter. Sorry, if you just bear with me, everyone, I will switch devices. Sorry about that. Okay, so that should be a better
We can't hear you now, Yusef.
Sorry, can you hear me now?
Quite faintly.
How about now?
Yeah, it's still quite quiet. That's better. That's better.
Okay, I'll try and get the mic close to my mouth. Hopefully you can hear that okay?
Yeah.
Yeah, okay. So this is a work in progress, as I said, and a lot of the ideas are still developing. A lot of the terms I'll be using might change, but it's produced some interesting results so far and has some interesting points to some interesting ways to use this in the future. So I'll just briefly explain the map you're looking at right now. This is for ADA, and it's based on the phase 1 habitat survey. And the different colors show how much the proportion for which that habitat class is contributing to ADA records relative to what they're contributing to all records. So these habitats in blue, less than a fifth of the ADA records are coming from that habitat relative to all the records that are coming from that habitat. The ones in red, they're contributing twice the amount of ADA records as you might expect from their total recording effort. And if anything about this isn't quite clear, I'll explain this in more detail now, going through it. So we'll just take a quick step back at motivations for wanting to make a habitat suitability map in this way, straight from the data, rather than, I'd say, a more traditional method of ranking the habitat classes beforehand and codifying the map that way. Obviously, we want to get a standardized method that's repeatable, objective, and we can quickly do for any species. We also want to make use of the data, of course. We're looking for ways to add more value to the data. We have more than 13 million records that a lot of effort has gone into producing. So if we can add more value to it, we want to. We do need to be careful, I suppose, about this last point, though, because we don't want to replicate effort that a lot of more academics are more fine-tuned. Many data analyses are already happening. Obviously, the various organizations for specific taxon groups are getting a much more specific and fine-tuned habitat, a fine-tuned picture on where species are and what habitats they're associated with anyway. So this is trying to strike some middle ground of something that can be produced quickly and can be widely distributed and widely accessible, and can be a good starting point for thinking about conservation or planning, etc. Of course, there's lots of challenges that that inevitably come with doing this. One is that habitat information isn't recorded as standard when we get records sent to us. As you know, the database comprises a large unstructured data set of records from all sources, so we have lots of confounding factors, and the records are telling us as much where people are recording from as they are about the habitat the species would normally choose to live in. This second challenge, of course, chiefly manifests as uneven recording between habitats. So the first step we would take to address these would be how we assign phase 1 habitat classes to records. So the data I put into this, I downloaded everything in the Aderin database last year before the Bumblebee project, and have been continuing to use that download for the current work. We've only used records at 6-figure grid reference resolution or finer, which gives us about 9 million records. the habitat data, we've used the phase 1 habitat survey of Wales, which is freely available on Clay, based on fieldwork, finished in 97, has complete coverage of Wales, and is obviously is in many ways getting out of date now, but is still probably the best complete coverage data set that we can get hold of, and also is a good thing to use to develop and illustrate a method. So we took each record, and assigned it a habitat class based on the habitat which occupied the largest amount of its grid reference. So in the map here, you see these big ones, big red squares, 100-meter squares, and they will pertain to some record. They're 6-figure grid references. This one here, for example, this has got a lot of different phase 1 classes intersecting it. Brown is bracken. This is semi-improved neutral grassland. Black is buildings, and some broadleaf woodland in green here as well. Whatever record this was would have just been given the habitat semi-improved neutral grassland because that occupied the largest amount of the square. Now, it wasn't necessarily the habitat that species was recorded from, which will cause some slight errors, but the hope, of course, is that any particular habitat is just as likely to get assigned by mistake as any other. So when you're doing this for a large number of records, over 9 million, those rough errors eventually get ironed out. The most basic question we could ask once we've done that is, which habitat classes are the species most frequently recorded from? So we could look at that for adder. Out of about 3,500 total adder records, just over 12% of those come from dry acid heath habitat. But we could also see that almost as many come from improved grassland habitat. So from this, just looking at this naive chart, you could, if you take it at face value, you could conclude that improved grassland is very good for adder. But of course, we're not accounting for that uneven recording here. So this is the same chart, and the scales change a lot because I've also put the percent area of Wales for each habitat. So we can see that improved grassland occupies almost 50% of Wales. So will inevitably generate a lot more recording, and that's something that we have to take into account. And we take that uneven recording into account by just seeing what percentage of all the records in all the database come from that habitat. That's our basic measure of total recording effort. So we can see that improved grassland, that's the gray bar here, giving the percentage of all records. Of the 9 million total records we're talking about, almost 30% of them have been assigned improved grassland habitat. It's still not being targeted by recorders at all, because we can see that because this gray bar is lower than the blue bar. It's not been sampled in proportion to its area, but it's still being sampled a lot more than any other habitat, and we have to take that into account. So we do that quite simply just by dividing the height of this orange bar, the proportion of adder records that are coming from the habitat, with the height of the gray bar, the proportion of all records that are coming from the habitat, making the basic intuition that if the species has no overall habitat preference for that habitat, if it's neutral to that habitat relative to all the others, then these should be roughly equal. So if adder had no positive or negative preference for improved grassland, you might expect, if it has about almost 30% of total recording, it should contribute 30% of adder records. And we can see that it doesn't, from which we infer a negative association. And just a couple of things about this graph here. Unimproved calcareous grassland does in fact have a blue bar. It's just too small to show up on this plot. It covers about 0.1% of the area in Wales, according to the old phase 1. We've also got this unrecorded category, and some areas of the phase 1 survey just were missed. No one recorded there, and there's no estimate of the area that covers, but we do know that about 3% of the records had didn't have a habitat recorded in the survey. And we can see that the orange bar is pretty much, exactly equal. So that's illustrating that sort of intuition. We have no a priori reason to expect ADA to have a positive or negative association with areas that were missed from the phase 1 survey, and we expect to see an association like that. So this ratio of dividing, the proportion of proportion of records for that species with the proportion of all records that come from a habitat, I've been calling encounter ratios, partly because I needed to give it a name because it was coming up a lot in this work. And it is simply the proportion of a species records that come from a habitat divided by the proportion of all records that come from a habitat. And here's that same graph illustrated as a table. So you can see, for example, dry acid heath, only 1% of all records come from that habitat, but 12% of ADA records come from that habitat. So you divide this 12% by that, we get an encounter ratio of about 11. Improved grassland, almost 30% of the records come from that habitat. 11% of ADA records come from that habitat. So it gives it an encounter ratio of 0.4. So values that are close to 1, we interpret that as a neutral association. It's not far off what we might expect by chance given total recording. Values a lot less than 1, we interpret as a negative association. And values a lot greater than 1, we interpret as a positive association. Now, it's a tiny bit more complicated than that, and I'm just putting this in for the sake of completeness. But for this work, I've calculated encounter ratios based on visits rather than records, where a visit is a unique 100-meter grid square date combination. It's a unique occurrence from where we got a list of records. It could have been one record or several from a grid square on a date. And there's about just over 1 million visits in the Adairn database. We do this to remove potential skewing effects of lots of duplicate records, because we often get, despite our best efforts, some records the same date. Many records in the same spot will actually be duplicates from different surveys. Also intense surveys with many fine-scale records from a small area. And a visit that yields at least one record of the focal species we call an encounter, which is where the term encounter ratio comes from. Now, I explained this based on the proportion of records rather than the proportion of visits, just because it was more intuitive. And now I'm just putting this in because visits will be talked about later, but you can still think of it exactly the same way. These maps show the relative proportion of species records that come from an area relative to the total recording effort that has been made to that habitat. So these red areas, could be something like dry acid heath, looking at the ADA table from before, which had an encounter ratio of 11. They're all greater than 2, showing a positive association. We have intertidal mudflats over here. You know, we do get some adder records coming from this area, but less than a fifth of the proportion of total records we get from that area. A lot of this blue stuff is the urban area of Wrexham. We get adder records coming from this phase 1 habitat class for all sorts of reasons. Partly sometimes it may represent gardens and good habitat, but we get less than a fifth of what we would expect if they were relative to the total recording effort that comes from that habitat. Oh, so, and I've made these groupings quite broad, as you can see. I haven't tried to, say that a ratio, something getting 10 times the adder records than you'd expect from its effort is better than something that's getting 5 times the adder records that you'd expect from its effort. And the reason that I've done that is because, of course, these ratios are showing us some measure of adder habitat preference, but they're also, affected by lots of confounding factors. Chiefly, that sampling effort varies between those habitats. In some of them, people are looking for adder perhaps more than others. Some habitats may overlap with areas that just happen to receive lots of monitoring. For example, particularly small habitats, which are very uncommon, are often found in nature reserves and get a lot of sampling that way. The habitat might have been misassigned from the process we talked about in the beginning. Particularly with an old data set at the phase 1, there may have been land cover change. So there's a potentially endless list of confounding factors to think about. Sometimes these confounding factors will make it more likely for a species to be encountered on a visit. Sometimes they might make it less likely. But one thing that we hope shouldn't change much between visits is the species' actual habitat preferences. It may be changing perhaps with climate change over time, but certainly on a much slower scale than all these other things are affecting it. So we'd hope that if we look at over visits, if these confounding factors are all affecting all the habitats roughly equally, a lot of their influence should cancel out. Now, I'm not saying that will necessarily be the case, and we should definitely take account of them, but it's a good reason to, but in general, we hope that, looking at large amounts of data, that these ratios will be, roughly valid. They're not worth throwing out completely. And we can do a quick reliability test for that, a very rough measure. We can say that species that are more generalist in their habitat preferences should have more encounter ratios close to 1, that is relative to more specialist species. Kate says 1210 was 20 minutes, so I'm just going to try and finish this quite quickly. So this is a hypothetical table for a generalist species with 5 habitat classes. We can see that the visits which return that species are roughly in proportion to the total visits. The species that are more specialist, they should have encounter ratios that are either very small or very large in relation to 1. So we can look at the data and see if that's true. This is a hypothetical example again. Before we do that, we just want to, we would convert any ratio that is less than 1, we'll take the inverse of it, because we're looking at the total distance from 1 overall. So we'll take the magnitude of that. So if it's positive, it stays the same. If it's less than 1, we take the inverse. So 0.5 is 2 times smaller than 1. 2 is obviously 2 times greater than 1. This 0.15 is about 6 times smaller than 1, etc. So basically, we can make the prediction that specialist species should have higher magnitude and counter ratios than generalist species on average. And we can quickly look if that's true. I've done this for a broad, rough selection of what I would call, picked out the hat of generalist species, generalist birds, generalist plants, insects. I have to throw a lichen in there. And these are the specialists. And hopefully, a lot of these names should be quite familiar to a lot of you. Have got roundleaf sundew as a plant specialist, bee orchid as a plant specialist. And I tried to make this as broad as possible. I didn't want to include just ridiculously specialized things like Snowdon lily, for example, to get a broad picture if this is generally true. And we can see from that overall, on average, these specialist species are having much higher encounter ratios. So I think I'll stop there because I'm running over time, but I think we've seen some maps, we've seen a rough intro to that method, and I think there's a lot more mileage in this and some more work will come from it in the future.
Thanks, Yusef, and sorry to have to rush you there.